We get a lot of questions about why we worry so much about flatness in some of our filters. We've actually, this is not new. We've been doing this since we started making filters and had to pay attention to it for special applications, particularly lasers and or other super resolution or mechanisms that even have very long beam paths. But it wasn't until through the lens turf systems were developed and released several years ago that this became much more mainstream and therefore had to become part of our pretty much catalog offerings. Discovered that the turf laser had to be very pristine and powerful in order to create the evanescent wave required for turf images. When the first systems were released, they used standard epifluorescence optics, and some of them worked, some of them didn't, and part of that was just luck of the draw. Some of those were flat enough, and some of them weren't. Most of them weren't. We had to get a system and go to work on it because what they were seeing in those days was images that looked much more like a standard fluorescence image and not a true turf image. And it turns out this was due to an astigmatism or distortion of the laser beam itself. This beam distortion can take on different shapes. It can be it can make a cross symbol. It can be oblong with waves. It can have shoulders. It can even look like lightning bolts and so forth. And this has to do with the fact that the laser is either passing through a substrate material or reflecting off of it that is not flat and or parallel. In the optics world, that's called reflected wavefront distortion or transmitted wavefront distortions. There are other distortions that can play into astigmatism as well. But we, after getting a microscope at Chroma and looking at the different optics in the beam path, discovered quickly that it was, in fact, the dichroic mirror that was causing the problems. The dichroic has to be very flat and it has to be held in place without distortion in order for the beam to get to the sample in the correct shape, homogeneity, and therefore power and so forth. So we discovered we could only do this with a 2 millimeter thick dichroic mirror, and since most cubes would not hold a 2 millimeter thick dichroic, and even if they did, many of the holding mechanisms in the cubes would create stress, we actually had to develop our own cube for this so that we could hold a 2 or 3 millimeter thick dichroic. In the process of this, we discovered that turf itself would not be true turf unless the laser beam reached the sample, and the requirements for that via the dichroic mirror was a 2 millimeter thick at minimum at a flatness of less than or equal to a half a wave per inch. So we built a cube that would hold 2 or 3 millimeter thick, and we built a mechanism that would hold them without stress. The testing of that shows that optics, if there's no optic in the beam path, the laser looks nice and round and homogeneous. And then if you use very flat optics, it looks identical. However, if you use optics that are not flat and or not parallel and or are stressed, then you see the astigmatisms. Now, it turns out that this can also happen on the emission side, that if you're trying to split an image to two different cameras or two halves of the same chip, you have to worry about the reflected wavefront of that splitting optic, that dichroic or that mirror. It has to be something around 0.5 waves per inch surface flatness or better for most of the camera systems that we have tested. So the bottom line here, and the reason that we talk so much about flatness, is if you're using lasers, super resolution systems, structured illumination, image analysis with quantification, or if you're splitting your image even on the backside to two different cameras, you have to pay attention to flatness of all the optics in the beam path. If you have any question, my name is Michael Stanley. My email is very simple. Thank you very much. Appreciate your time.